we have now reached a critical juncture in our study of groups. So we're going to be talking about the isomorphism theorems today. We talked about homomorphisms before, and we even introduced the concept of isomorphism, so you should already know what that means. However, there are several very important theorems about isomorphisms that we're going to introduce today with the help of normal subgroups and quotient groups. So last time we proved this theorem at the end. We said that if F is a group homomorphism of G into H and N is a normal subgroup of G contained in the kernel of F, then there exists a unique homomorphism F tilde from the quotient of G by N to the group H, such that F tilde of the left coset of N and G by A is equal to F of A for all A in the group G. Moreover, the image of F tilde is equal to the image of F. The kernel of F tilde is equal to the quotient of the kernel of F by the normal subgroup N. And F tilde is an isomorphism if and only if F is both an epimorphism and N is equal to the kernel of F. And then we had this diagram which helped us understand exactly what this theorem is saying, right? So given F, it's a homomorphism, and given pi, which is the canonical projection map, which we also showed is a homomorphism, in fact it is an epimorphism, then there exists unique F tilde, which is a homomorphism from the quotient to H, right? And such that F tilde composed with pi is equal to the map F. Now I cannot understate the significance of this theorem. It doesn't have a name, but all its corollaries do, and today is devoted solely to the corollaries which follow immediately from this theorem, and they are called the isomorphism theorems, or the group isomorphism theorems. Our first corollary is also known as the first isomorphism theorem, and it says that if F is a group homomorphism from G to H, then F induces an isomorphism. G quotiented by the kernel of F is isomorphic to the image of F. We know that image of F is a subgroup of H, and the kernel of F, we showed before, is a normal subgroup of G, which means this quotient is well defined, and this quotient is indeed isomorphic to this image subgroup. The proof is simple. So we're going to refer casually to the previous theorem as our main theorem of this unit. And so in the main theorem, if we just simply set N equal to the kernel of the homomorphism F, right, then we automatically get our result, right? We said that F tilde rather are induced maps. If we have G going to H by F, and then we have the projection map mapping us from G to G quotient kernel F. And we said there exists a unique map, F tilde, which is also a homomorphism, going from this quotient to this, right? Now, if we only consider the subgroup of H to which F actually maps elements from G, this is the image of F, of course, then this map is indeed onto, because every map is onto its image. So this is an epimorphism. And we also have that N is equal to the kernel of F by supposition, so that F tilde, by our previous theorem, is an isomorphism. Our next corollary is going to be what's called the third isomorphism theorem. I'm doing the third before the second because it's a little bit simpler, I think, a little bit more intuitive, and there's no logical dependence between the second and third, right? They're just independent theorems. So, it says that if H and K are normal subgroups of group G, such that K is a subgroup of H, then H quotient K is normal in G quotient K, and G quotient K quotient H quotient K is isomorphic to G quotient H. So it's almost like, even though this has nothing to do with multiplication in the sense of fractions and cancellation, it's almost like these K's cancel out and we get just the G and the H. So it is exactly what we would want to happen. All right, before we dive into this proof, I just want to make a little comment that we've come a long way to get to this point. We have a long way to go, but we've come a long way. Because we're finally to the point where I cannot do the proof in one take without a piece of paper. So consider yourselves making serious progress on learning group theory. All right, first we want to consider the identity automorphism from G to itself. That is exactly the map which sends each of the elements of G to themselves. All right, now this is going to induce a map alpha from the quotient group G quotient K to the quotient group G quotient H. And alpha is going to be given by alpha of GK, left coset of K and G by some element small g, is equal to GH. Now I claim that alpha is going to be an epimorphism here. Why is this so? Well, again, consider this identity mapping. G mapping to itself implies that since there always exists a G mapping to G, namely itself under the identity map. So that if we consider this left coset, we can always, since this is a left coset of H in the group G by this element little g, there always exists for any such little g we choose to represent this coset. We can just map this under the identity mapping. We can say the pre-image of this coset is the coset of K and G given by that same element. All right, now I'd like to take a moment to examine our assumptions. I was rewatching this footage, and even though I got this proof more or less from a very trustworthy textbook, I thought about it and I realized the details are not quite there. And because this is an elementary treatment of group theory, I really want to be 100% transparent with you on these proofs. Make sure that every step is clear. So toward that end, I want to demonstrate for you that alpha is a mapping, because it would be absolutely terrible if it satisfied operation preservation, right? So that we would be led to think that it's a homomorphism, but it fails to even be a function. So how would alpha fail to be a function? Well, alpha would map one element to not a unique element, but perhaps several elements. What's to say that for two different G1, G2 in the group G, we have G1K is equal to G2K, so these cosets are the same, but perhaps G1H is not equal to G2H. Can these two things happen at the same time? Personally, I don't think that it's obvious that it can't, so let's justify it. Alright, so assume that G1 and G2 are elements of the group G, such that G1K is equal to G2K. So we're talking about the same coset, but generated sort of in two different ways here. Alright, well, this implies, if you'll recall, or rather there's an if and only if, that G1 is left congruent to G2 mod K, right? Or congruence mod a subgroup. And this is true, of course, if and only if G1 inverse times G2 is in the subgroup K, right? Now, because G1 inverse times G2, this product, is in the subgroup K, and in the statement of the theorem we assumed that K is a subgroup of H, and thus a subset of it also, then we must also have that G1 inverse G2 is in the larger group H, and this is true if and only if G1 is left congruent to G2 mod H, right, by the same ideas up here, and this is true if and only if G1H is equal to G2H. So it is indeed true that these two cosets being generated by different elements, or this one coset rather being generated by two elements, does not matter because these two being equal implies that these two are equal, and so our function is single valued. However, I think there's an important lesson here, because if you look at this, you're not thinking oh, the multi-valuedness or single-valuedness of this function depends upon this weird product G1 inverse G2. I just don't think it's completely obvious. It's always really important that you look at every assumption. You don't want to be assuming that something is a homomorphism when it fails to even be a mapping. So always pay attention to the basics. Alright, so we see that it's onto. Now the question is it a homomorphism? Well, alpha of G1k times G2k, right, these are two arbitrary elements of this quotient group, is going to be equal to, since k is normal in G, multiplication of cosets is well defined, and we can say that this is equal to alpha of G1 times G2 times k, right? And by definition of alpha, this is going to be equal to G1, G2 times h on the left. And then, once again, h is normal in G, so that multiplication is well defined, and we can separate this to form G1h times G2h. And of course, this is exactly the property we were hoping to prove. It's operation preserving, and it's onto, so that we see alpha is indeed an epimorphism of this quotient group onto that quotient group. Now we're interested in which elements map to the coset h, right? So h is equal to alpha of gk, where this is just some arbitrary element of g quotient k, is equal to gh, right? This is true if and only if g is an element of h. So that is to say that all those elements from here which map to the identity coset in G quotient H are exactly given by those left cosets of K and G for which G is an H. In other words, the kernel of the mapping alpha is equal to the set of all HK such that H is in the subgroup H, right? And this is exactly the definition of H quotient K. So we see that the kernel of alpha is equal to the quotient group H quotient K. Alright, now since alpha is a homomorphism, the kernel of alpha must be a normal subgroup of the domain, which in this case is G quotient K. But we just showed that the kernel of alpha is none other than H quotient K, which is to say that H quotient K is thus normal inside of G quotient K, and we conclude that G quotient K quotient H quotient K is a well-defined quotient group. Alright, there's one more step we have left in proving the third isomorphism theorem. So by the first isomorphism theorem, since this is the domain of alpha, G quotient K quotient the kernel of alpha is isomorphic to the image of alpha, right? This is the statement of our first isomorphism theorem. However, we know a couple things. We know that the kernel of alpha, we've already shown, is equal to H quotiented by K. So all that's left is to decide what is the image of alpha. Well, we said that alpha is an onto mapping. It's an epimorphism. So G quotient K mapping to G quotient H, if that's an onto mapping, then the image is G quotient H. In other words, it's equal to G quotient H, and if we just state this in one line, this says that G quotient K quotiented by H quotient K is isomorphic to G quotient H. This is the third isomorphism theorem. Our next corollary is going to be the second isomorphism theorem, or as I like to affectionately refer to it, the one you're probably not going to memorize. You should know of its existence and be able to refer to it and use it as necessary, even prove it ideally, but I wouldn't bother memorizing it. So it says the following: if K and N are both subgroups of group G, with N being normal in G, then k quotiented by the intersection of n and k is isomorphic to nk, the join of n and k, right, quotiented by n. And we showed last time that these two quotients are well defined in the sense that this is normal in this, and this is normal in this. So now we are showing that these two things are isomorphic. To prove the second isomorphism theorem, we're going to start with the observation from last time that n is normal in the join of n and k, right? Now, if we call iota from k to the join of n and k the inclusion map, so let me write that out for you, inclusion map. And this is exactly that map which just sends every element of k to the element of the join of n and k, which is itself. So it sends every element to itself because k is contained in nk. So if iota is this inclusion map and pi from, in this case, nk to nk quotient n is the canonical projection, which we've discussed before, then we can consider their composition, right? So we showed before that the canonical projection is indeed a homomorphism. In fact, it's an epimorphism. But regardless, so iota should also be clear that this is a homomorphism. It's a map between groups which sends every element of a group to itself contained in a larger group. So it should be fairly obvious that iota is also a homomorphism. And we know that the composition of two homomorphisms, which in this case is pi composed with iota, is also a homomorphism. So we're going to consider this map, and this is going to be from, if you go k to nk, nk to nk quotient n, we're going to have a map from k to nk quotient n, and this is indeed a homomorphism. All right, now consider an element x which is contained in the kernel of this map, pi composed with iota. By definition, this is a subgroup of the domain, which is k, so this implies that x is contained in the subgroup k. Now, since iota of x is just equal to x, and we have pi of x is equal to xn, then pi composed with iota of x is also just going to be equal to xn. So that if x is in the kernel, this is equal to the identity coset, or just n. And this implies, this is true if and only if, really, x is in the normal subgroup n. Now, since x has been shown by supposition being in this kernel to be in both k and n, we say that x is contained in the intersection of k and n. Now, suppose instead that x is an element of n intersect k. Then we have the following. N is therefore in n, right? And we also then have that xn is equal to n. In other words, pi of x is equal to n, the identity element in this quotient group. Now, since iota just maps things to themselves, we have that the preimage of this must be itself, so that pi composed with iota of x is equal to n, or the identity coset. In other words, x is therefore in the kernel of pi composed with the inclusion map. Now, since we have shown in both directions that x in this intersection implies it's in the kernel, and that x in the kernel implies it's in this intersection, for arbitrary x, we can conclude that these two sets are the same. That the kernel of pi composed with iota is equal to none other than n intersect k. Now, by the first isomorphism theorem, we have that k quotiented by kernel of this composite map is going to be isomorphic to the image of the composite map, right? We just showed that the kernel is equal to n intersect k. So all that remains is to discover what the image of this map is. Next we have that n is normal in nk, which means that for all a in nk, we have an is equal to na. Now, if we restrict this to just those elements A in the subgroup K, which is contained in the join of N and K, then we get that Kn is equal to Nk for all elements of the subgroup K. Now, in particular, this means that for all N in the normal subgroup N and for all K in the subgroup K, there must exist an element eta in the normal subgroup N such that Nk is equal to K eta. And what this means is that for an arbitrary element in Nk quotient N, so we have Nk quotient N, this is going to look like an element from Nk, which is going to look like just little n times little k times N, right? It's a coset of N in the join of N and K by this arbitrary element of the join of N and K, which in general is of this form for arbitrary N and K. A lot of N's and K's. So that, but we said that since we have this normality relationship, we can substitute this for that, and we get that this is equal to the coset of N in Nk by K eta, which if you do this in this order, this means that we have an element of eta times n. This is going to be just the coset n, so that it becomes of the form kn. Now, kn is just pi of k, and because the inclusion map does exactly that, it includes, then this is equal to pi composed with iota of the element k for some k in the subgroup k. Now, if pi composed with iota is an onto mapping, in other words, it's an epimorphism, then we have that the target is in fact the image, so that this is equal to nk quotient n. Now, by the statement of the first isomorphism theorem, we have k quotiented by n intersect k must be isomorphic to the join of n and k quotiented by n. The second isomorphism theorem, ladies and gentlemen. Now, I'd just like to summarize these three theorems before we move any further. So here they are, folks, the isomorphism theorems, or at least this is the first, second, and third isomorphism theorems, and usually what we refer to collectively as the isomorphism theorems, although occasionally a fourth is thrown in, which I will give to you at the end because it's also an important theorem. So the first one tells us about how homomorphisms naturally induce isomorphisms through their kernels. The second one tells us about the relationship between a normal subgroup and the join of it in another subgroup, and how this is related to, of course, k quotiented by the intersection of the two subgroups. The last one basically says that if you have a chain of normal subgroups in your group G, so K is contained in H is contained in G, then the various quotients you can form are indeed related, as one would suspect. They have a very natural relationship. So I can't understate the importance of these theorems, as well as the fact that they're all corollaries of what we were calling the main theorem earlier, right? These are all sort of just footnotes to that theorem. Of the three of these, I would of course say that the first isomorphism theorem is the most important, and you see this sort of logically as it is used to prove both the second and third isomorphism theorems, but also it just has a huge range of applications, and we'll see that. We're going to go through and give examples of each of these so that you can get a good idea of what they're really saying. And yeah. Alright, now it's time to learn by example. So we're going to harken back to the particular examples that we learned about in the videos on homomorphisms. And we're going to explore those same groups and those same homomorphisms again, but now in the light of the isomorphism theorems. Hopefully this will deepen our understanding. Starting with the first isomorphism theorem. We gave an example at one time of a homomorphism from the additive integers to the additive even integers. And we specifically called it phi of m is equal to 2m, right, for all m in this domain. Now we want to consider what isomorphism does this homomorphism induce? Well, by the first isomorphism theorem, we have that z plus quotiented by the kernel of phi is isomorphic to the image of phi, right? This is the statement we want to focus on here. What is the kernel? The kernel in this case is the set of all elements which map to 0, and the only element which gets mapped to 0 is 0 in this case. So quotiented by just the group generated by the identity or the trivial group. And this is going to be isomorphic to the image. What is the image? Well, for every even integer, you can find some odd integer which multiplied by 2 is equal to that integer, with the exception of 0, but 0 just gets mapped to 0. In other words, this is an onto mapping, so that this is isomorphic to 2z. So here we have this following statement. We have that the additive integers quotiented by the identity element is isomorphic to the even additive integers. And in fact, when you quotient by the trivial group, this is essentially the same as doing nothing, so that these two groups are isomorphic. And this is exactly what you would expect, that the integers and the even integers under addition are exactly structurally the same. For our second example, consider the map given from the symmetric group on 2 symbols to the symmetric group on 3 symbols, or letters if you like. We gave this map before where we said that phi of the identity, I'm going to use the same notation as in the homomorphisms video, is equal to the identity, and phi of sigma 1, 2, the element which switches symbol 1 and symbol 2 is equal to sigma 1, 3, right? The element which effectively swaps symbol 1 and symbol 3. We considered this homomorphism before. Now we want to consider it in light of the isomorphism theorems. So, if we have S2 quotiented by, what is the kernel here? The kernel is all those elements which get sent to the identity. In this case, this is just the identity. So once again, it's going to be quotiented by the trivial group. And we have that this is isomorphic to the image of this map, which is going to be, what is the image? Well, the image is going to be the group generated by sigma 1, 3. Recall that sigma 1, 3, if you apply it twice, is going to switch symbols 1 and 3 twice, so it is the identity mapping, so it includes both those elements. So we're safe. This, by the way, is isomorphic to Z2. There's isomorphisms all around here. And of course, again, we have the trivial group here, so that this goes away, and you have S2 is actually isomorphic to this subgroup of S3, which is an interesting statement, and we're getting that just by knowing that there's a homomorphism going from S2 to S3. All right, now let's consider the map from the set of all linear fractional transformations, as we defined it before, to the general linear group of 2 over the real numbers, right? Dimension 2 over the real numbers. And we defined this to be phi of AZ plus B over CZ plus D to be equal to the matrix A, B, C, D, right? And we said that AD minus BC, the determinant, is non-zero by supposition. This was our homomorphism we talked about before. Now, what does this mean if we look at L quotiented by the kernel of phi is isomorphic to the image of phi? The kernel is going to be set of all elements which map exactly to the identity matrix. And the identity matrix is A equal to 1, D equal to 1, and B and C equal to 0. So if these two are 0 and those two are 1, we're going to get that it's just the element Z. It's just a singular, I shouldn't say singular, single linear fractional transformation. And this is isomorphic to the image, and the image in this case is going to be the whole group. GL of 2R sometimes is also denoted with a subscript GL2 or GL2 of R. There's all kinds of notation floating around, but we see this. And because this is the trivial subgroup, once again, L quotiented by the trivial subgroup is isomorphic to L, so that we get an isomorphism between these two groups. And so we didn't actually have to show directly that these two groups were isomorphic. All we had to do was find a homomorphism between them, and then by the first isomorphism theorem, that homomorphism phi induced an isomorphism between them. All three examples so far have been this case. It's trivial, where the kernel is just the identity element or the trivial subgroup of the domain. But even in this trivial case, it still gives us valuable information because it still induces an isomorphism, and in particular, it tells us about how the domain and codomain are related as groups. All right, next example is going to be the homomorphism gamma from, once again, the general linear group to the multiplicative real numbers, excluding 0, of course. And it's given exactly by gamma of some matrix M is equal to the determinant of M, right? This is the determinant map, and we said that that was a homomorphism before, right? So what does the first isomorphism tell us? Once again, we have the same story. GL2 quotiented by the kernel of gamma is isomorphic to the image of gamma. What is the kernel here? Well, what is the identity element? Since we're talking about a multiplicative group, it's going to be 1, not 0, so that we're concerned with all 2 by 2 matrices with real entries whose determinant is exactly positive 1, right? In other words, it's going to be the special linear group in 2 dimensions over the real numbers. So this is a slightly less trivial case than before. And this is isomorphic to the image of gamma. All right, so what is the image of gamma? Well, if we look at the identity matrix, right, and we multiply this by some real number c, then the determinant of this matrix is going to be equal to, if you look at this, it's going to be equal to c squared, right? Which is going to give, so we can obtain any positive determinant just by scaling the identity matrix. Now similarly, we could obtain any negative determinant by scaling this matrix by any real number c, right? This is going to be equal to negative c squared. So what we see is that any non-zero real number has a manifestation as a determinant of a 2 by 2 matrix in the general linear group, which means that this map gamma is onto, and the image is thus the real numbers under multiplication without 0. So now this is an interesting statement here. The general linear group, quotiented by the special linear group, is isomorphic to the multiplicative real numbers. For our last example of the first isomorphism theorem, let's consider the map we once considered before from the multiplicative complex numbers, right, excluding the origin, to the positive, strictly positive multiplicative real numbers. So we have x in the multiplicative real numbers such that x is greater than 0. And we said that f given by f of z is equal to the modulus of z. We talked about this and we proved before that it is indeed a homomorphism from this group into that group. So now the first isomorphism says, theorem says that this first group, quotiented by the kernel of f, is isomorphic to the image of f. We say this every time because I want to burn it into your skull, right? You should have this isomorphism theorem at the very, very least memorized. So what is the kernel in this case? Well, the kernel is going to be those set of complex numbers who have modulus exactly 1. In other words, their distance from the origin is 1, and we're going to have exactly the unit circle, which is sometimes denoted as S1, or S1 in its complex number manifestation, so I'll write it that way. So we have the complex numbers without 0, multiplicative group, quotiented by the unit circle, is isomorphic to, and what is the image set in this case? The image is all those elements which get mapped to. In other words, all those real numbers, positive real numbers, for which there is a complex number with exactly that modulus, and that's going to be all of them, right? Because we can pick, if we consider a radial line, not including the origin here, we can pick a number in the complex plane that is anywhere on this line, and thus any distance, any positive distance anyway, from the origin. We can't do 0, of course. So that means that every element here gets mapped to at least once, in fact infinitely many times, because we can pick such a line in any direction, right? So there are infinitely many of them. So this is definitely an onto mapping, so we get that this is isomorphic to, again, those multiplicative real numbers which are exactly positive. This is to say that the complex plane, or rather the punctured complex plane, so without the origin, quotiented by the unit circle, so the punctured plane without respect to circles centered at the origin, think of it that way, is isomorphic to positive real numbers. In other words, if this point is identified with all points on the circle that has equal radius from the origin as that point, then what do you really have? All you have is a circle for every distance for the origin, right? In other words, you have this radial line, which is exactly that. Now for the second isomorphism theorem, I'd like to hone in on one particular example. So this is our abbreviated form of it. So let's set G to be equal to the general linear group of 2C, so the complex numbers here, and let's set K to be equal to the special linear group of 2 over the complex numbers, and N is equal to the multiplicative complex numbers scaling the identity matrix, the 2 by 2 identity matrix. In other words, this is equal to the set of all matrices A0, 0, A, such that A is a complex number and A is non-zero, right? So for all, we'll say M in GL2, we'll abbreviate it, and for all elements which are all of the form x0, 0, x in the multiplicative complex scalings of this 2 by 2 identity matrix, what we're going to show is that this group is normal in that group, right? So we're going to have M times x0, 0, x times M inverse, right? So the question we have to ask is this product in this subgroup? All right, so this is equal to M x times the identity matrix times M inverse, right? And we can instead write this as M times x times identity times m inverse, right? Which is just going to be equal to m times x m inverse, right? It's the identity matrix. And this is going to be equal to x times m inverse, just by the properties of things. Remember that x is a scalar here, is equal to x times the identity matrix when those cancel out. And of course, well, first of all, I should note that m is invertible because it's in GL. And this is, of course, in these scaled identity matrices, right? So, indeed, this is a normal subgroup of that. Now, simply by the statement of the second isomorphism theorem, this gives us the following. So we have K, which is SL. So SL2 of C quotiented by the intersection of SL2 of C with this group N, which is exactly that, is isomorphic to the join of N and K. So SL2 of C join, recall that's the other way to write the join. Join with that, quotiented by, of course, N, which in this case is the multiplicative real numbers scaling, or complex numbers scaling the identity matrix again. Now this is not a super clear statement to read, so we're going to simplify it a little bit more. Alright, so this intersection is simply going to be the positive identity matrix and the negative of the identity matrix, right? These are the only matrices which look like this, 2 by 2 over the complex numbers, which have determinant exactly positive 1. So that simplifies that a bit. Now, what is the join of these two? That's also a relevant matter. Well, the special linear group, recall, is just the reduction of the general linear group down to those matrices which have exactly determinant positive 1. But if we're multiplying such a matrix by another matrix which doesn't change it in any matter except for an overall phase factor, right? Because we have the identity matrix multiplied by that. So m times x times the identity for some complex x is just going to give us the scaling, a complex scaling of our matrix M. In other words, we recover all possible determinants again, all non-zero possible determinants, so that this join is going to be GL2. So if we write this a little bit neater, we see that SL2 of C quotiented by this set is isomorphic to GL2 of C quotiented by multiplicative real numbers scaling the identity matrix. So what does this actually mean? Well, if we take all our elements of SL2 and then we say we're going to identify any two elements of this group which have which are negatives of each other, right? So that's what we're doing here, and this actually has a special name. It's called the projective special linear group over the complex numbers. Here we're saying let's take any of these complex valued matrices, right, with that are invertible, and we're going to identify any two of them which are scalings of each other by some complex number, some non-zero complex number. This also has a name. It's a very special group. It's called the projective general linear group over the complex numbers. So by the second isomorphism theorem, we've just shown an incredibly important fact. The projective general linear group is isomorphic to the projective special linear group in this case, and this is an unusual and awesome fact. So consider the following groups. Consider Z and its subgroups, 3Z and 12Z. So all the additive integers, all the additive integers which are multiples of 3, and likewise with multiples of 12, right? These are 3 different additive groups. This one is contained in that one, is contained in that one. And we know that the normality relationships we desire hold because they are abelian groups, right? So they're sort of trivially normal in larger groups. So the third isomorphism theorem applies, and we can say soundly that z quotiented by 12z quotiented by 3z quotiented by 12z is isomorphic to z quotient 3z. What does this mean? Well, what is z quotient 12z? We talked about this kind of quotient when we talked about the quotient group, right? So z quotient mz is equal to addition modulo m, right? So this is z12, right? And this is going to be, well, this is going to be isomorphic at least to z4, and this is going to be isomorphic to z3. So we have z12 quotiented by z4 is isomorphic to z3, and indeed this is exactly the relationship that we would expect to hold between these groups. Now we've talked a couple times about the quaternion group, which we referred to as H before, and we've seen both of these subgroups in different examples. So both of these are going to be normal in the quaternion group, so that the third isomorphism theorem applies. So let's see what it says. So this is the statement of the third isomorphism theorem applied to our quaternion group here. So if we identify elements based on their sign, right? So any 2 elements with opposite sign are now considered as one element, one coset in the quotient group. And then if we do the same thing in this smaller subgroup, then what we get when we take the quotient here is an isomorphism with the quotient of h by this bigger subgroup, plus or minus 1 plus or minus I. Something that's interesting about the quaternion group is we can form these quotients because every non-trivial proper subgroup of the quaternion group is normal in it, which is an unusual property for non-abelian groups. Another notation for H is Q8, since it's the quaternion group, it has 8 elements, and this is isomorphic to Z2, and this is isomorphic to Z4. So you basically have, although this is a little bit fast and loose, that Q8 quotient Z2 quotient Z4 quotient Z2 is isomorphic to Q8 quotient Z4. I said sort of, in a weird sort of isomorphic way, not strictly according to the letter of the law here. So our final theorem today, which I'm going to state without proof, is called the correspondence theorem. It is usually considered alongside the isomorphism theorem, sometimes called the fourth one. So what it says is that if F is an epimorphism of groups from G on to H, then the assignment K mapping to F of K defines a one-to-one correspondence between the set of all subgroups K and G which contain the kernel of F and the set of all subgroups of the group H. I want to draw your attention to one particular fact, and that is that under this said one-to-one correspondence of subgroups, we find that normal subgroups in G are paired with normal subgroups in H, so that whenever we have an epimorphism like this, it induces a relationship between the normal subgroups of G and the normal subgroups of H. And now we can finally see at the end of the isomorphism theorems, and then culminating also in this theorem, the correspondence theorem, that normal subgroups play very nicely with homomorphisms, as I said. And it's not immediately obvious why we would have introduced cosets, and then not obvious why we introduced normal subgroups, and not obvious why we introduced quotient groups, right? They're sort of abstract concepts. But the further you build, the more powerful we see that these notions are. And they may not be very natural to us. They are natural to group theory. They are very central and natural concepts when we talk about things with an identity and inverses and closure and this binary operation stuff, right? So it's not always obvious. I guess there's a little bit of a math life lesson, I don't know. It's not always obvious why we introduce definitions, and very often the most confusing definitions are essential to the subject and get us really, really far. Topology is a great example of this, where you have, just weird starting definitions, but then it's super powerful. And it's often the case that if we start from intuitive definitions, we end in a place that is not, we didn't get very far, that our natural idea of what should be dealt with, right? What concepts should be central is usually wrong. It's counterintuitive, and we later discover what the real deep ideas are. And normal subgroups are a deep idea in group theory, and this is only illustrated once we've reached these isomorphism theorems, some of the most important material in introductory group theory. Thanks for watching.